Hi folks, and welcome back to Math with Captain Rod. The purpose of this video is to give you an example of how to use methods of calculus to optimize functions. So in this case here, what we're looking at, the example we're going to go over is we got little Jim here, and Jim's got a sheep that he needs to fence in. And Jim can only afford 500 feet of fence. So the million-dollar question here is how big a rectangular pen can Jimmy create to fence that sheep in if he uses the neighbor's fence line next door? So the idea here is Jimmy's going to take this roll of 500 feet. He's going to make some sort of rectangular configuration to put around this guy using some of the neighbor's fence line to do so. So the million-dollar question now is how much area here can he enclose? What's the largest area that can be enclosed using this 500-foot roll of fence and the already existing fence line next door? Now, the first thing to recognize is what is it we're trying to optimize. And in this case, what we're trying to optimize is the area. The area that our sheep gets to graze in. Now, the dimensions of our pen here are unknown, so we might start by assigning variables to the unknown dimensions. So we might call maybe this dimension x and then this dimension y, and if this is a rectangle, this would be another x. The area of this pen would then equal x times y, because this is a rectangular pen. And this is what we're trying to optimize. Now right now, this is a two-variable problem. X and y are conceivably both functions. So before we can optimize this function, it would be nice to get it down to one variable. We can get it down to one variable using this fact. We know that there's only 500 feet of fence available, which means the distance from here along this path to here, if we use all our material, will equal 500. Now when we go from here to here, we've used x amount, and then y amount, and then another x amount. So the 500 feet is equal to 2x plus y. X plus y plus another x, and there's your 2x. Now, I'm going to go ahead and leave the units out when I solve this. I can solve this for y. Y is going to equal 500 minus 2x. Just keep in mind that that's 500 feet minus 2x feet. And now anywhere we see a y, we can sub this quantity. So the area can be written x times y, which is equal to 500 minus 2x. And now we have a function for area with x only. Now, we'll notice now that this function is quadratic, right? Because it's 500x minus 2x squared. If I were to just sketch a quick graph of this function real quick, I'll do this over to the side here. We science people, we love our graphs. Math people too. Area against x. I'm going to take note that this thing has a 0 at 0, because if I put a 0 here, this whole product is 0, so I know it goes through this point. Also, another 0 I can get by setting that equal to 0. And if I do that, I'm not even going to bother writing this down, but if I set 500 minus 2x equal to 0 and solve for x, I believe we're going to get 250 out of that. Now, looking at this, since it's 500x minus 2x squared, the minus sign is indicating this is a parabola that opens down. So this function must look something like this. Now, talk about the domain of that function. Functionally, this thing is defined everywhere. When you talk about domains of functions, you have the mathematical things that restrict your domains, like division by zeros and square rooting negative numbers. But in applied problems, you also have physical reasons to restrict your domain. So in this example right here, this length x has to be some positive value. This problem doesn't make sense really for negative values of x. And also, x can't be more than 250, because if it were, we wouldn't have any left for y. So this thing, by the time we apply those restrictions, this function is only really defined from 0 to 250, which is why that's all I drew in the graph. Now we're trying to find the maximum value for the area. Well, the maximum value for the area is right here. So, and I'm going to call that A max. And that's what we're trying to find. And the dimensions, the x value, that'll get us that. Now you might be able to guess what dimensions we can get just from the geometry here, but I'm going to talk about the calculus approach for finding this. The area is a maximum at this point, and that point is what's called a relative extreme value. That's a relative maximum. And if you're not familiar with relative maximum, I go back and check out my video on relative extrema where I go through that. This point can be found because the tangent line has zero slope. And that's the fact that we're going to use to find that point. The tangent line has zero slope, which means dA dx equals 0 right at that point. So here's my value for A. And I'll just write this right here. dA dx is therefore, and I'm differentiating this function, 500 minus 4x. And now what I'm going to do is set that equal to 0 and solve for x. So we're going to have 500 equals 4x, or in other words, x equals 125. And I'm going to go ahead and put the units on that. Those were feet. So the value of x that is going to optimize the area or give us the largest possible area is 125 feet. We can get the value of y by going back and taking note of 500 minus 2x equals y. So that's going to be 500 minus 2 times 125 equals y. And this is going to be 500 minus 250 equals y. And so y is going to be, I believe that's 250 feet. So dimensions of 125 by 250 should give us the largest possible area. And the value of that area we can get by putting x into really anywhere in here, or actually right here now that we know x and y, but I'll go ahead and just sub it right here. That's going to be 500. I'm going to run out of room here, but let's see, 500 feet times x, 125 feet, minus 2 times 125 feet squared. What I'm going to do here is wait for one of my little helpers here to give me a value. Somebody please run that and give me a value for that function. 500 times 125 minus 2 times 125 squared. I know it's a little hard to read. I apologize for that. 31,000 what? 31250 square feet. I'm going to wait and make sure we get another opinion on that. Just to be sure. Yeah. Okay, so now if it's wrong, it's your guys' fault. Great. Okay, so little Jimmy here is going to spend his money on this 500-foot of fence. He can fence in 31,250 square feet of fence, given these dimensions. 125 by 250. And by taking advantage of using the neighbor's fence line. So the purpose of this video is to go through an example of how to optimize some sort of function. And although most problems are somewhat unique, here are the things that are common to all of them. One, you have to figure out what you're trying to optimize. In this case, this young man is trying to optimize the area. How much area can he get for his little lamb here with only 500 feet of fence? Once you know what you're trying to optimize, here's our first step here. You have to write a function that describes what it is you're trying to optimize, what you're trying to maximize or minimize. Typically, it's very common for that function to have two variables. You typically then try to reduce it to one variable using some fact from the problem. Like over here, we know that we only have 500 feet of fence available. Third step, you should graph your function and identify where on the graph you want to be. Usually when you're optimizing, although not always, but usually your optimization point will be a relative extreme value. So You find those by looking for where the derivative of your function is 0. I would call this problem done, but as a final step here, you probably should ensure that you found the correct spot by looking at the second derivative. In this case, we would look for where a double prime was positive or negative, and I'm not going to do it because I'm out of room. But if you calculate a double prime and you apply it at x equals 125 feet, you're going to get a negative number out of it, meaning that the slope is decreasing, meaning that you have found a relative maximum instead of a relative minimum. So those are all steps to optimization problems that are reasonably common to all of them. You don't necessarily need to do the very last step, particularly when you have a graph. If you have a graph, this one's fairly obvious that that's a relative maximum. So hope this video helps demonstrate these concepts. Have a great day.